Our next speaker is Nils. His presentation will be about algorithm hardware or operating system co-design for heterogeneous system on chips. Nils completed his PhD at Dresden. So welcome back. And he introduced the M3 architecture with his PhD thesis, which initially focused on heterogeneous systems. And since 2019, he works as a principal researcher at the Barkhausen Institut in Dresden, where the work on the M3 system architecture is actually continued based on a larger team of operating system and hardware researchers. And his research interests include the boundary between hardware and software, programming languages, and microkernel-based systems. And the floor is yours.
Yeah, thanks for the introduction. Yeah, I guess my talk is one of the few outliers here because it's actually not on RIOT. Instead, it's on M3, which is hardware operating system co-design for heterogeneous systems on chip. And yeah, the motivation is that we nowadays have lots of complexity, both on the software side and also on the hardware side. Like on the software side, we have huge operating systems like Linux, for example, that on the one hand we want to use because they have all kinds of functionality, but on the other hand, they tend to have security issues and for some use cases, of course, also too large. We also have challenges on the hardware side, for example, through heterogeneity, like accelerators, for example, and also since we have more and more untrusted hardware components. But let me go a bit more into detail here. So software complexity first. As I said, we have these huge monolithic operating systems that are a problem in some aspects. And one solution for that is using a microkernel-based system. So the idea that you split up your system into isolated components. A study also showed that this seems to work. So if this study was looking at all the CVEs of Linux and found that if we would have built it as a microkernel-based system, then 96% of the CVEs could have been reduced in severity and 40% could have been eliminated. So microkernels seem to be a good fit if you want to build more secure systems. But we also have more complexity on the hardware side nowadays, because we have more and more heterogeneous systems, like we have systems that have accelerators for specific tasks that give us more performance and better energy efficiency. But on the other hand, that of course makes the system more difficult to build, to use, and so on, because we have now a diversity on the hardware side, especially for operating systems. This is a challenge because if you want to fully integrate these accelerators, you can no longer just have the shared single kernel running on all cores, because it will not run on some of the cores, right? So the operating system needs to be prepared for this diversity in the processing elements, or whatever you want to call them, in the hardware platform. Second of all, we also have more and more untrusted components since our systems become larger, and that means not a single vendor will be producing all the components. So we have third-party vendors that that deliver some of the components, and of course the question is whether we want to or can trust them. And for example, there was this Broadcom incident a couple of years ago where a bug in the Wi-Fi chip was able to, or allowed a remote attacker to completely take over the system. So this is, for example, something that we need to avoid, obviously. The other type of problems are these side channel issues that we have since at least a couple of years ago, but probably much longer than that, where in some way or the other, an attacker can leak private data from basically another address space, from another virtual machine, from an SGX enclave, whatever. So through the security boundaries that the core actually should provide. And the thing is that these issues have been lurking in CPUs for many years, and of course also due to the complexity, they become prominent, become visible now. And this raises the question whether we can still trust these cores to properly enforce boundaries between software components on top of them. Okay, so our approach to these problems is that we split both the hardware and the software into isolated components. So like take the ideas from microkernels to split things up into components and apply that to the hardware side as well. So how does that look like? So as I said, it's a hardware operating system co-design. And the idea is that we take existing components at first as they are, like cores, accelerators, network on chips, caches, and so on, because we don't think it's feasible to modify them. And instead, what we do is we add a new hardware component next to them. So you can see we have this tiled architecture here with different tiles containing different kinds of processing elements. And in each of them, in each tile, we have now this trusted communication unit, this TCU, which is a new hardware component that we add. And this TCU is both for isolation and communication. So you can isolate tiles with the TCU from each other, and you can selectively allow communication. On the operating system side, you can see here it looks like this. So we have the kernel running on a dedicated tile, and the kernel it's only the kernel running on this tile, and the applications and services are running on the remaining tiles. So it's a kind of unusual OS design. But it fits well for heterogeneous systems because we cannot assume to run the kernel on every tile, because some tile might be a fixed function accelerator, for example, not running software at all. And therefore we have this operating system design. And with this design, we reduce complexity, coming back to the motivation, in 3 different ways. So at first, we build it as a microkernel-based system, getting the advantages from that by splitting the software part up into different components. We have this TCU as a uniform interface for all of these tiles. So this reduces the challenge of the heterogeneity that we have and want to have also a bit, because it becomes easier to manage for the operating system and also easier to use for the applications. And last but not least, we have the TCU acting as an isolation layer. As I said, we isolate these tiles from each other, which allows us to integrate untrusted hardware components as well. So for example, we could have an untrusted accelerator in such a tile. And since the TCU is the only way for the accelerator to talk to tile external resources, we can just control the TCU to control what the accelerator can access in the system. And this is why we can integrate untrusted accelerators or any other component in a reasonable and secure way. Okay, going a bit more into detail. So how does this TCU work? As I said, it's a communication device, so it provides means to communicate between tiles. To do so, it provides so-called endpoints. And these can be configured at runtime to different types of endpoints. First, we have a memory endpoint, so you can have access to a piece of memory, like in the DRAM, for example, and then you can issue DMA requests to read or write from this memory region in DRAM. Second of all, we have message passing functionality in the TCU, and for that we have 2 types of endpoints. We have receive endpoints that allow you to receive messages from the senders, and they are then put into a receive buffer in your own memory. And we have send endpoints that allow you to send messages to one of the receiving endpoints. We also have a reply feature. This comes now back to the microkernel-based system. So in a microkernel, you have all these different kinds of components for services, drivers, and so on. And therefore, you have to have a lot of these remote procedure call-like communication patterns, right, with a request and then a response. And therefore, we have also a reply feature in the TCU that allows you to reply on a received message exactly once back to the sender. Okay, then a bit more about the isolation. As I said, the TCU isolates tiles from each other. And this can be seen as an additional protection layer, because in some cases, of course, we have a core that provides user mode, kernel mode, has virtual memory, and so on. And therefore, you have isolation on this core as well, and can run multiple components on the core and isolate them from each other. And then we have an additional protection layer in the TCU that protects to the rest of the system, so everything beyond the tile boundary. But in some cases, it's also the only isolation layer. Like, for example, if you have a simple accelerator that doesn't have any protection, then the TCU is the only means to protect it from the rest of the system. Yeah, and an important thing here is only the kernel is allowed to establish these communication channels between TCUs. But at the same time, the user tiles, where the applications and services are running, can use these established channels. And therefore, at the setup time, the kernel is involved and is, for example, building a message passing channel between two tiles. But afterwards, the kernel is no longer used because the tiles can communicate directly by just using their TCU. Okay, so far about the hardware part. Now to the operating system. So the operating system is also called M3, which either stands for microkernel-based system for heterogeneous many cores. So you can count these 3 M's in there, or L4 plus minus 1, because it's also inspired from L4, at least conceptually. But it's implemented from scratch, mostly in Rust these days, but also there's a bit of C++ left. Yeah, it's a microkernel-based system, and this is why drivers, file systems, use network stacks, and all these kind of things are implemented on user tiles and are not part of the kernel. The kernel's main responsibility is to implement capabilities to manage the permissions in the system, and with this build communication channels between the TCUs. So it's the manager of these channels, you could say, and then we have the TCU as the enforcement part. So the TCU is enforcing these permissions in the sense that it says, okay, if the message size is too large, then an error will occur and it will be denied. Or if you just have read access to a certain memory area, then trying to write to it will fail. And therefore, we have this split into management and enforcement between kernel and TCU. An interesting property here is also that the kernel is mostly independent of the other tiles in the system, because the kernel is just running on its own tile and it doesn't really care how the other tiles are working. Like if you take our file system and 3FS, for example, if that's an ordinary software component or if it's implemented on an FPGA, let's say, the kernel doesn't really care about that. It cares about the TCU and its interface and so on, but not how the actual components are implemented. And this is why we can also more easily support such heterogeneous systems. Okay, in terms of prototype platforms, we have 2 platforms. We have at first the Gem5 simulator, which is a quite flexible and modular simulator platform that we have extended by the TCU and also by some accelerators. And this allows us to do early prototyping and just try out more easily and quicker new ideas that we have. And then second of all, we have an FPGA-based hardware platform that is built by the hardware people at the Barkhausen Institut. And this is where we go to the next step to build it actually in hardware and run it on this FPGA. Also have a more detailed picture of the hardware platform that we put on this FPGA. So you can see it's a RISC-V based platform. We have all these different tiles that you can see here organized around the routers of the network on chip. And there are also a few special tiles, as you can see here. For example, we have 2 DDR4 interface tiles that have a memory controller in the tile and then go to off-chip DRAM. Then we have 1 tile that has a NIC attached that allows us to do network measurements. And we have another networking tile, which is this UDP-IP thing, which is a UDP-IP stack implemented in hardware that allows us to load stuff onto the platform. So with this, we can load programs onto the other tiles and set the system up and so on. We use the Rocket and Boom cores here as the 2 core variants that we have. So Rocket is a more simple in-order core, and Boom is the out-of-order variant of that. They have both 2 times 16 kilobyte L1 cache and 502 kilobyte 2 cache. And the TCU in here has 128 endpoints in the current implementation. So just to give you a rough idea how the hardware looks like. Then we have, on top of that, various research projects that we already did based on this concept. So the first paper is the overall idea. Then we have one about accelerator integration and how we can make them run autonomously. And we have also looked at the scalability with Semporize, for example. We have one on multiplexing cores with M3V. And also 2 others on real-time and looking at the isolation properties of this system architecture. Yeah, we have, of course, also still ongoing projects. So we have, for example, one project on tile-based trusted execution environments that we just submitted to SPLOS. We are working on remote attestation with sealed memory. We also have activities in the real-time direction to see how what real-time properties M3 can provide and how we have to kind of change the design to make that better. We also have a project that runs Linux on one of the tiles, so where Linux is just an untrusted component running on a user tile, and we can reuse device drivers from it, for example. And we are also at the Barkhausen Institute building real silicon chips. And of course, we want to run M3 on that. So this is also ongoing, although we have not managed to make M3 really running on that, because it's actually doing that all by yourself, like sending it to the fab and doing all the packaging and so on, turns out to be rather complicated. And yeah, but I think we are getting there. I don't know how many students are here, but just to mention that we're also always looking for students. So if you think this is interesting, just approach us and we will certainly find some topic in this area. Maybe also in collaboration with RIOT. I mean, I don't have concrete ideas, but maybe that makes sense. To conclude the talk, so M3 proposes a new system architecture based on this hardware operating system co-design, where we have this TCU as a simple and uniform communication and isolation component, and building a microkernel-based system on top of that. And with this, we try to reduce the complexity of systems in 3 ways. First, by using the microkernel approach, to split software components up into multiple ones. Then by using this TCU as an isolation layer to integrate untrusted hardware components, and also to use that as an abstraction layer to make heterogeneous systems more feasible. With this, thanks for your attention, and I'm happy to take your questions.
Thank you very much for the presentation. Okay, we have questions here already. Okay. Did you try to make this work for microcontrollers as well?
Not yet, no. And I mean, it would make sense if we have multiple of these, right? But M3 is always building on the assumption that you split your platform up into multiple components, like multiple cores or something. But if you do that, then it might work, because M3 doesn't need features like the memory management unit and user kernel mode. It can just be a program that runs bare metal with all these features.
Because I think if you do, there's work by X5, a RISC-V company, who specifically for microcontrollers developed something which they call a multi-zone approach, which is similar. There's different names, all different names that you use, but the conception is the same. The problem is, I believe, why they failed is because it requires changes to all the applications, to everything involved. Because you need to interface with that sort of messaging interface, essentially. ECU is messaging interface, and all the applications need to change. That's a big ask. That can be a showstopper. At least it was for them, but they may have failed otherwise, which I don't know.
It can be a challenge. So we, of course, also have that problem. I mean, we have compatibility layers, like we have the muscle C library, for example, that you can then use to build your normal application on top. And this is translating then to the M3 specific APIs. Or the Linux tile might also be one thing to use. But yeah, it can be difficult.
There was like a course or something, right? And then you install the system, one is running the kernel, and then there's some networking, and then some file system, and then something, and then there's the application. It seems to me it's like, okay, there's not much left for application, and all the other courses, but the idea was I think that it's like burning a lot of like potential performance.
If you construct it like that, yes. But we had this, so show this slide here. We have this efficient and scalable co-multiplexing work a couple of years ago, exactly for this reason. Because, as you said, if you just have one application or one software component per tile, this is pretty limited. And therefore, we have this multiplexing approach that you can run multiple applications on one tile. Of course, having then weaker isolation between them than between tiles. But that's the trade-off that you then have to make. But then you can, use that more efficiently.
Back just to where you showed Daniel. To which extent is the kernel micromanagement, say, communication with the network? Does the concrete card just get access to the network and does the authorization to read and write like packages, or is this more like the one tile requests from the kernel permission to send a single packet and then get confirmation back when that packet is sent and then it means, or anything in between?
It's the former. So if you get a communication channel, let's say for message passing, then you have a send endpoint that allows you to send messages to one specific receive endpoint. And then you have a message size, a maximum message size that you can use. And then you can send messages. So what we also have to limit that a bit, because there is some problem, of course, because if you don't have anything else, you might just DOS attack other components, right? You can just message it all the time. And therefore we have a credit system that works like you have a receive buffer and then you give out credits for the slots in the receive buffer. And let's say one sender just gets one credit, then you can send one message, and then you have to wait for getting the credit back from the receiver. And this way, the kernel is out of the game after the setup phase, and we have this system in place to make that secure.
Do we have further questions?
Not.
Yeah. So one of the issues for microkernel are always an IPC and the overhead for also that. Now adding additional hardware into the pad still not IPC, especially if the schedule stuff could introduce a lot of additional overhead, right? So have you measured that? I know that you only implemented the FPGAs, which is not quite that old.
Well, it could, but actually it acts also as an IPC accelerator, right? Because we now have a hardware component for IPC, especially for cross-tile IPC, which is pretty slow in microkernel-based systems. So if you go cross-core, right, that can be, 5 to 10,000 cycles per IPC or per round trip. And with this, we are much better with the TCU because we have this dedicated component doing it. And we also don't need interrupts and so on. So this is much cheaper. It's more in the order of 500 cycles. On one core, it still has overhead, right? If you just run both components on one core and multiplex between those, this has overhead. And therefore, we still have this usual trade-off that you don't want to make that too fine-granular, right? Your components and your the amount of IPC. But we also have performance measurements where we show that even if we do that, even if we have multiple components like file system, pager, and all these things, we are roughly competitive to Linux in at least the use cases we measured. So it doesn't always mean that you are slow.
Anyone wants to ask more questions? Okay, I think enough questions for you then. Thanks for the presentation.